So that was a preamble. Next, we're going to discuss the role of symmetries in classical field theories. And after that, in the next lecture, we're going to move on to their quantum descendants. So a very central result, in quantum field theory is Noether's theorem. So Noether's theorem, what it does is that it relates symmetries of your action or Lagrangian to conserved quantities, such as energy, momentum, charge. Phi be a classical field, and let alpha be a real continuous parameter which parameterizes an infinitesimal transformation of the field such that the field goes to phi plus, say, alpha times del of phi, such that the action of the theory of the phi field remains invariant. So for each of these symmetries, there exists for each of these continuous transformations or symmetries of S a conserved current. So this is Noether's theorem. By the way, the parameter alpha has to be a space-time independent parameter, which means the symmetry transformation is a global transformation or a global symmetry. If this parameter A, alpha, becomes a function of space-time, it becomes a local parameter, then Noether's theorem does not apply. So how do we go about proving this theorem? Well, by the statement, if I change phi to phi plus alpha del of phi, because the action remains invariant, that means the Lagrangian can change at most by a 4-dimensional total derivative. Because now if I do a 4-dimensional integration over all space-time, let's say call it M4, then this thing just becomes, under this transformation, the first term is the same, but the second term, we have M4, d4 of x alpha, the 4 divergence of j. But the second term, we can write this as a boundary integral over M4. We are using the 4-dimensional Gauss's theorem. And then we get d3 of x, and then the alpha can be factored out because it's a constant. And then we have some outward pointing normal. So if this is my space-time M4, then the boundary is given by this red, and N4, N mu is the outward normal. So this is N mu. It can be space-like or time-like. So N mu, and then it's going to be dotted with J mu. And then because what we assume is that our fields are such that, everything goes to zero at infinity, large enough. So at large enough boundaries of space-time, this J is going to go to zero. So this term then goes to zero. And therefore, we find that the action remains invariant under such a transformation. But the Lagrangian doesn't have to be. It can change up to F4 divergence. So how do we derive this conserved charge or current? So, under the transformation where phi goes to phi plus alpha del phi, and this is a physical phi, so they satisfy the equation of motion, then, the Lagrangian changes by L. Okay, let me just work out what the change in the Lagrangian is. It's going to be delta L. The Lagrangian is a function of the field phi. So there will be a delta phi term. But the Lagrangian is also a function of the first derivative of the field. So it'll be also, there'll be a term which is the derivative of alpha delta phi. Now, what we can do is that the second term, we can do an integration by parts. So we get del by del phi, del L by del phi, alpha del of phi. And over here, what we can do is we can do an integration by parts. So we get del by del del mu of phi times alpha delta phi, and then minus del mu of del L by del mu phi. And then outside there'll be alpha delta phi. Right. So, but what we see is that these two terms are just proportional to the Euler-Lagrange equation. And since we are assuming that our field satisfies the Euler-Lagrange equation, in other words, our fields are on shell. If they're on shell, then these terms vanish by Euler-Lagrange equation. And therefore, the change in the Lagrangian is given by alpha, which is a constant, so we can factor it out, times del mu, and then we have del L divided by the derivative with respect to the derivative of the field times del of phi. So, but we saw that this is the for divergence. So that means that what we can write is that the for divergence of J is equal to del mu del L by del mu of phi times del phi. So that means that if I now define a current which is small j mu, which is big J mu minus this guy, which is the derivative of the Lagrangian with respect to del mu of phi times del of phi, then this current, small j mu, is conserved. And therefore, this is, if I write it in non-covariant language, this is nothing but J0 by dt plus divergence of the three-dimensional current J. In other words, this is the continuity equation. And therefore, we can integrate this over all space, and then by the usual argument that you're familiar with, I'm sure, from quantum mechanics, we find that there's a conserved quantity, say Q, which is called a charge, although it can be energy or momentum or anything else. It's a generalized name. It's so the integration over all space of J0 is, of course, J0 is given by d cubed x big J0 minus del L by del phi dot del phi, that this is a conserved current, that is del Q, sorry, conserved charge, that is del Q del T is 0, because you can show that this is nothing but this equation. So this is Noether's theorem. It not just tells you that given a continuous global symmetry of your theory, that there is a conserved current and a conserved charge, it also gives you what that charge is. So let's look at some examples. So example number 1, let's look at that complex scalar field. So the complex scalar field has the Lagrangian Now, this has a symmetry that the real scalar field doesn't. And the symmetry is that if I multiply phi by, say, some phase where alpha is a constant, then phi star gets multiplied by the opposite phase. But we see that because alpha doesn't depend on space-time, the Lagrangian doesn't change. For alpha small, we see that this means that its del of phi is I alpha phi, and del of phi star is minus I alpha phi star. Oh, by the way, if there are more than one, say, fields involved in this transformation, then we have to have a sum over the field and the corresponding parameter. And then in the end, in the current, we will have a sum over the field as well. And here we can think of the field phi and its complex conjugate as independent fields. So, this is basically what we get. And then, but because the Lagrange is invariant, that means that, the big J mu is 0. That doesn't change. And therefore, we can work out what delta L of del mu of phi del of phi is, and that's just I times del mu phi star, and then times phi. And then del L by del mu phi star times del of phi is minus I del mu of phi times phi star. So therefore, we find that the current is J mu I times delta mu phi star times phi minus phi star del mu phi. Now, if I look at the 0th component of this thing, that should ring a bell. It's phi star dot phi minus phi star phi dot. This is the current that we derived for the Klein-Gordon equation, hoping that it would give us an equation of continuity which we could interpret as a continuity equation for the probability. But because the J0 component was not positive definite, we couldn't give a probabilistic interpretation of the Klein-Gordon current. So this is exactly the same current. So we recognize this as the Klein-Gordon current. So now after quantization, what we'll see that this current is actually doesn't have a probability interpretation, but it has the interpretation of the charge current, the electric charge current, because this field is a complex scalar field, and therefore it has particles and antiparticles, and therefore what this current does is that it just measures, the electric current, and J0 is just electric charge density, and therefore it doesn't have to be positive. So quantum field theory, rescues the the Klein-Gordon equation, because it gives a coherent interpretation to the current, because it doesn't try to interpret that current as a probability current. Okay, now number two is, let's just take any scalar field theory. It doesn't have to be the real or the complex scalar field. It could be either of those. And the Lagranges that we have seen so far are invariant under space-time translation. Because suppose we take space-time and translate it by a constant about a mu, then of course what we see is that these derivative operators don't change. So we see that the Lagrangian, how does the fields change? Well, the field changes to, say, phi of prime of x. This is the transform field. But this is, if there's a minus sign here, there should be a plus sign over here. So suppose we have a field configuration. So there's x, and there's a phi, and this is some field. And what we do is that we translate x to x prime. We define x prime to be x minus a, where x is equal to a. We get x prime is 0. So this is going to be the origin of my x prime coordinate system, and this will be the field phi prime. So now what we're going to do is that we're going to ask, what is the value of, say, phi prime at x? So phi prime at x. So let's just take, for the sake of argument, x to be 0. So that means that this will be equal to phi at a, which is x plus a. Okay, so we see that if I do this translation, the new field is related to the old field in this way. And so using this, what we find is phi prime of x, of course, is phi of x plus a. And if I take a to be infinitesimal, then I can do a Taylor expansion, and this becomes phi of x plus a mu, the derivative of phi with respect to x mu. And because the Lagrangian is also a scalar, so we see that the Lagrangian will also change in the same way, where we have the Lagrangian at x, and then we have a mu, the derivative of the Lagrangian with respect to x mu. But this we can rewrite as L of x plus a nu times the derivative with respect to mu, and inside the Lagrangian we get a delta, a Kronecker delta, lambda mu nu of this. So that, this is, so here we have 4 parameter a mu. So there would be 4 conserved currents. So each of these guys would be J, and the current index is, we have, this should be nu. So the current index is going to be given by mu upstairs, but which current it is is given by, say, nu. So let me just use nu here. So this is the four-dimensional index that is a current, and this is labeling which current it is. Right. So now if I plug in the values of, delta, so this is basically going to be my delta of phi, then I'm going to get 4 currents. So each current is going to be labeled by an index mu, and because each of them is a current, 4 current, therefore there will be a space-time index nu, and so these will be delta mu nu times the Lagrangian density, and then we'll have delta L by del mu of phi times del mu of phi. So, so what are the conserved charges? The conserved charges, as you remember, is we take the 0th component of the current and integrate over all space. So if we take the 0th component, say we take nu equals to 0, and we can raise the mu index upstairs and then integrate it over all space. And so this is all space. So we have 4 charges, sorry. We have 4 conserved charges. We are calling P mu. So P0 will be the Hamiltonian, and this is conserved because of the translation under because of the parameter A mu. That is, the energy is conserved because our system is symmetric under translation in the time direction. Similarly, the 3 other conserved charges, they are the momentum, the 3 momentum, and they are conserved because our system is invariant under a spatial translation. So therefore, we see that Noether's theorem is telling us that energy and momentum are conserved because of the symmetry of our space-time. So of course, our Minkowski space is also symmetric under rotation. So, and you'd be able to show that because of the invariance under rotation, a quantum field theory, if a quantum field theory is invariant under rotation, then the angular momentum is conserved. And because what is the conserved quantity under the boosts? Under the boosts, if our quantum field theory is invariant under boost transformations, then the corresponding conserved quantities are essentially the center of mass of the field. That the center of mass of the field, it propagates at a constant velocity.